Right now, the phone sitting in your pocket is probably doing, well, absolutely nothing.
Right, it looks completely dormant.
Exactly. The screen is black, it seems totally dead. But in reality, it is silently shouting your exact location to nearby cell towers. It's scanning your neighbor's Wi-Fi routers and, authenticating its identity to a corporate server 3 states away, all in the background.
Yeah, I mean, the independence of the modern smartphone is entirely an illusion.
Right. We tend to think of these devices as standalone, self-contained magic boxes, mostly because that's how they're marketed to us.
Oh, absolutely. But the piece of glass and metal you stare at all day is really just a node.
Yeah.
The second that baseband radio powers up, you're participating in a global infrastructure that is relentlessly complex, ruthlessly efficient, and deliberately hidden from the end user.
And dragging that hidden infrastructure out into the light is our mission for this deep dive. For you listening right now, we are going to demystify how your phone talks to the world, and perhaps more importantly, how the corporate world talks to your phone.
We want to bypass the shiny user manual and extract the actual mechanics of your everyday tech.
Right, we're getting into the weeds. And to do that, our sources today aren't like consumer tech blogs. We are pulling directly from IT certification training notes, specifically the CompTIA A+ materials.
Yeah, this is the foundational curriculum used to train the engineers and system administrators who actually build, manage, and secure these environments.
It's the real deal.
It gives us an unfiltered look at the rulebook. We aren't analyzing what a marketing department wants you to believe about your privacy or, connectivity. We're looking at the strict technical protocols that dictate how data moves, how physical location is tracked, and how organizations exert control over hardware they don't even own.
Okay, let's unpack this. Because to understand the control layer, we first have to understand the physical reality of the connection. The training materials start with the concept of cells. We throw the term cell phone around constantly without visualizing the logistics,
Right. It is a literal geographical grid.
like actual zones on a map.
Exactly. The physical landscape of a city or a country is carved up into intersecting zones, and each zone is blanketed by a specific antenna broadcasting on specific radio frequencies.
It's kind of wild.
Think about the engineering miracle required just to maintain a connection as you move through those zones.
Hmm?
If you're driving down a highway at 70 miles an hour, streaming audio or holding a voice call, your device is rapidly moving from one geographical cell to the next.
Right, it's hopping between powers.
Yeah, and the network has to anticipate your trajectory. It negotiates a new connection with the approaching tower, transitions your live IP session to the new frequency, and drops the old connection all in milliseconds without dropping a single packet of data. That handoff is the foundational premise of cellular architecture.
And the pipeline for that data has completely mutated over the years. The historical timeline in the sources highlights the progression from 3G back in 1998, which, finally enabled baseline features like GPS tracking and primitive video conferencing.
Right, the early days.
Yeah, and then to 4G LTE pushing like 150 megabits per second, and then LTE advanced doubling that. But the jump to the 5G rollout around 2020 seems fundamentally different.
Oh, it's a massive leap.
The sources cite speeds of 100 to 900 megabits on standard frequencies and up to 10 gigabits per second on millimeter wave frequencies. But I have to push back on how this is usually framed.
Okay, how so?
Like, is 5G genuinely a technological paradigm shift, or is it just the telecom industry selling us a wider pipe so we can download 4K movies faster? It feels like we just went from a garden hose to a massive water main.
What's fascinating here is that the width of the pipe entirely changes the architecture of computing.
Wait, really?
Yeah. For decades, mobile devices were severely constrained by the bottleneck of wireless transmission. If an application required complex computation, the local processor inside the phone had to do the heavy lifting.
Which drained the battery and made the phone super hot.
Exactly.
Yeah.
But 5G's massive throughput and ultra-low latency remove that bottleneck. It shifts the heavy processing from the local hardware into the cloud. It's really the catalyst for the Internet of Things, or IoT.
Oh, I see.
You can now deploy millions of low-power sensors, smart meters, industrial monitors, and they don't need massive internal brains. They just need a 5G radio to instantly dump raw data into the cloud for processing and receive the computed answer back in real time.
So the device isn't just faster, its brain is essentially being externalized, and the phone itself becomes this incredibly versatile routing hub.
Right.
The CompTIA notes dive into how standard 802.11 Wi-Fi integrates into this too. We all know about Wi-Fi calling for when your 5G signal dies inside a concrete building, but the hotspot functionality is where the networking gets interesting.
Yeah, the hotspot feature is crucial.
A lot of people call the hotspot feature a bilingual translator, but looking at the mechanics, it's much closer to a logistics hub. Like, the 5G connection is the freight train bringing a massive cargo of data to a warehouse, and the Wi-Fi radio is the fleet of local delivery vans taking that data the last few feet to your laptop or tablet.
That is a highly accurate way to visualize network bridging. Your phone is simultaneously maintaining two entirely different networking protocols.
Doing both jobs at once.
Yeah, it's authenticating and routing traffic back and forth between the cellular provider's wide area network and the localized, private 802.11 network it just created in your living room.
Which is pretty incredible.
Though, as the certification notes emphasize, the telecom carriers are acutely aware that you're turning their mobile endpoint into a commercial router, which is why that specific routing capability often requires explicit carrier permission or, a different billing tier.
Right, they want their cut. And because the conduit has become so wide and so fast, knowing exactly where that conduit physically exists becomes a massive priority.
Location is everything.
We navigate, we tag photos, we track deliveries, all relying on GPS. But the actual mechanism of the global positioning system, which was originally built by the Department of Defense, is wild. The sources specify that for your phone to lock in its precise longitude, latitude, and altitude, it requires a direct line of sight to at least 4 satellites simultaneously circling the Earth.
Yeah, the math behind it, called trilateration, is elegant but demanding. A single satellite broadcasts its position and a highly precise timestamp.
Okay.
Your phone receives that signal and calculates how long it took to arrive. That draws a massive sphere of probability around that satellite. Your phone knows it exists somewhere on the surface of that sphere.
Makes sense.
Then a second satellite draws another sphere.
Yeah.
Where those two spheres intersect creates a circle. A third satellite narrows that circle down to two specific points, one usually floating in space, the other on the surface of the Earth.
So 3 satellites get you a location on a 2D map. Why the absolute necessity for the fourth?
Timing synchronization. Radio waves travel at the speed of light. If the internal clock on your smartphone is off by even 1,000th of a second compared to the atomic clocks on the satellites, your calculated location on Earth would be off by hundreds of miles.
Wow.
So the fourth satellite provides the geometrical intersection required to perfectly synchronize your phone's clock, locking in your precise 3D location, including altitude, down to the meter.
Here's where it gets really interesting, though. If the fundamental requirement of GPS is a clear, unobstructed line of sight to 4 satellites floating in space, how does my Maps app still perfectly track my walking path when I'm 3 levels deep inside a subterranean concrete parking garage?
Because it's not using the satellites at that point.
Right. The radio waves from space certainly aren't penetrating thousands of tons of rebar.
They aren't. And that illustrates the redundancy built into modern location services. Your device doesn't just give up when it loses the sky. The IT notes highlight 2 critical fallback mechanisms.
The first one.
The first is Wi-Fi network mapping. As you walk through that parking garage, your phone's Wi-Fi radio is passively scanning for the unique MV addresses of any wireless routers installed in the building or surrounding offices.
Even if you aren't connected to them.
Even if you aren't connected to them, it takes those identifiers and references them against massive global databases maintained by companies like Apple and Google. They've spent years mapping the exact physical locations of millions of static Wi-Fi access points.
So it is entirely crowdsourcing its physical location based on the stationary hardware around it.
Exactly. And if there isn't a single Wi-Fi router in the garage, it falls back to cellular tower triangulation.
How does that work?
The network measures the exact time it takes for your phone's handshake signal to reach 3 different nearby cell towers. By comparing the time difference of arrival at each tower, the network geometry can calculate roughly where you must be standing, even deep underground.
Which perfectly transitions us to the most localized protocol of all Bluetooth. If 5G is the global highway and Wi-Fi is the local neighborhood, Bluetooth is the digital ecosystem of your physical body.
Yeah, your personal bubble.
Headsets, smartwatches, vehicle infotainment systems. The notes detail the pairing process, moving a device into discoverable mode and using a PIN to establish the connection. But it isn't just about punching in a 4-digit number. It's a cryptographic handshake.
Right. That initial PIN exchange is simply the authorization to generate a complex asymmetric link key.
Okay, so it's doing complex math in the background.
Yes, the devices exchange public keys, compute a shared secret, and store that link key in their local memory. Once that mathematical relationship is established, you never need the PN again.
You just turn it on and it works.
You power down the headset, turn it back on 3 days later, and the devices instantly recognize each other's stored cryptographic signatures and bridge the connection automatically.
So let's look at the picture we've painted so far. We have a device capable of pulling gigabits of data from the cloud, mapping its location down to the meter using atomic clocks and localized MC addresses, and constantly broadcasting cryptographic handshakes to local hardware.
It's a powerhouse.
Because it acts as such a powerful tracking node, the network has to be absolutely certain who is operating it. And historically, that identity has been tied to the SIM, the subscriber identity module.
The physical SIM card is a fascinating piece of legacy technology. It's essentially a microcomputer.
Wait, really? It's that smart?
Oh, yeah. It has its own processor, its own RAM, and its own storage. Its primary function is to securely hold the International Mobile Subscriber Identity, or MSI, along with the cryptographic keys needed to identify and authenticate you to the carrier's network.
But the physical reality of the SIM has always been a bottleneck. If you change carriers or travel internationally, you are physically hunting down a paperclip, popping out a tiny tray, and swapping one microchip for another. Have you ever had to hunt down a paperclip just to change your phone number? It's the worst.
It is entirely archaic, but the sources highlight the evolution to the eSIM, the embedded SIM. And this isn't just a digitized version of a card.
Right.
It is a permanent, secure element soldered directly onto the phone's motherboard. The transition to EUICC, which is the technical standard for eSIM, completely changes how cellular provisioning works.
Because you don't need the physical mail anymore.
Exactly. Instead of a carrier manufacturing a physical chip and mailing it to you, your phone connects to a secure server and downloads the cryptographic profile over the air. The friction of physical distribution is completely eliminated.
But the secondary consequence of the eSIM is the true game changer here. The notes point out that a single embedded chip can store multiple profiles simultaneously. You're no longer restricted by how many physical trays a manufacturer can carve into the side of a phone. One physical baseband radio can now hold multiple distinct identities.
You can have a personal cellular contract with one provider and a corporate profile managed by a completely different provider running simultaneously on the exact same hardware. The operating system just virtualizes the dual connection.
So what does this all mean? Because that multi-profile capability is the exact flashpoint where our deep dive shifts into the corporate realm. Organizations have realized that their employees are walking around with supercomputers capable of massive data exfiltration, precise location tracking, and multiple hidden network connections.
It's a security nightmare for them.
Exactly. Businesses are terrified of their proprietary data living in that environment. So they implement a management layer. The notes outline the ownership models, starting with BYOD, bring your own device.
Right. The BYOD model was initially incredibly popular because of the capital expenditure savings for the company and the convenience for the employee.
Everyone wins, supposedly. Supposedly. The employee owns the hardware, pays the cellular bill, and doesn't have to carry a separate, clunky corporate phone in their bag.
But the friction there is privacy. It feels a lot like renting out a room in your own house to your boss.
Yeah.
If I am using my personally owned phone under a BYOD model to access corporate email or internal servers, the immediate fear is, can my company just read all my personal text messages?
Right.
Or track my weekend GPS coordinates? Or accidentally wipe my family photo album if I decide to quit the company?
If we connect this to the bigger picture, the architecture of modern mobile operating systems was specifically redesigned to solve that exact paranoia. IT departments use a mobile device manager, an MDM.
Okay, an MDM.
When a BYOD device enrolls in an MDM, the phone's operating system implements strict containerization. It uses a hypervisor to create a secure, encrypted sandbox on the storage drive that is entirely walled off from the rest of the phone.
Oh, so the corporate data lives in a vault. Exactly. The IT administrator only has visibility and control over the vault. The MDM cannot access the memory blocks where your personal text, browsing history, or photos are stored.
That's a relief.
And if you leave the company, the MDM sends a selective wipe command, which simply deletes the encryption keys for that specific corporate vault. The corporate data vanishes instantly, and your personal data remains completely untouched.
That makes the BYOD model sound much more palatable, But the CompTIA notes heavily contrast that with Cope corporate owned, personally enabled.
Yeah, Cope flips the power dynamic entirely. The enterprise purchases the hardware, owns the asset, and provisions the cellular contract.
So it's their phone.
Yes. They allow the employee to use the device for personal tasks, making personal calls, downloading personal apps, but the device is legally and technically corporate property.
So the containerization is reversed. The company owns the house. They're just letting you sleep on the couch. And because they own the root hardware, the privacy expectations for the end user drop to zero, right?
Basically zero, yes.
The MDM policy applied to a COPE device treats it the same way it would treat a corporate desktop workstation sitting in an office cubicle. There is also CYOD, choose your own device, where employees pick from a pre-approved menu of hardware, but it generally operates under similar corporate-owned management principles.
Right. Regardless of the acronym, all of this control filters back to the MDM.
And the IT certification materials actually walk through the interface of the MDM console. I like to think of it as the puppet master's dashboard.
When an administrator logs in, the overarching view is staggering. They see an inventory of every connected node in the enterprise fleet. They can pull hardware identifiers like the IMEI, view the exact OS version down to the patch level, monitor battery health, verify compliance status.
They see everything.
And from that console, they construct configuration profiles, which are essentially XML files packed with system-level commands, and push them over the air to the entire fleet.
And the level of local override those profiles possess is fascinating. The notes detail the security enforcement. Like, the MDM can mandate complex alphanumeric passcodes, force local storage encryption, and require multi-factor authentication before a user can even unlock the screen.
Standard security stuff.
Right, but the restrictions tab is where you realize how deep the hooks go into the operating system kernel.
Oh yeah, the restrictions policy supersedes the local user's authority. An MDM can remotely disable the physical camera hardware. It can disable built-in applications like FaceTime or Safari. It can even restrict the device from pairing with unrecognized Bluetooth accessories to prevent data exfiltration.
The notes explicitly mention they can turn off Siri. I mean, imagine angering your corporate security officer and they just remotely lobotomize your digital assistant.
It happens.
But what caught my eye was the logistics of data synchronization. The MDM controls over-the-air, or OTA, syncing. An admin can set incredibly granular rules like forcing Microsoft Exchange to sync continuously, but restricting iCloud backups to only occur under certain conditions. The specific example in the source material states an MDM can force all enterprise application updates or massive data backups to occur only when the device is connected to an 802.11 Wi-Fi network, completely disabling cellular syncing for those specific tasks. But think about that from the user's perspective.
Okay.
If the device has a 5G connection with gigabit speeds, why would an IT admin care if my corporate calendar or an app update pulls over cellular versus Wi-Fi? Isn't synced data just synced data?
This raises an important question about the hidden financial logistics of enterprise technology. When you operate a single consumer device, you generally don't think about background data consumption. But an IT administrator is managing a fleet of thousands, sometimes tens of thousands, of devices.
So it's the scale of the operation.
The scale dictates the policy.
Hmm.
Enterprise cellular contracts are incredibly complex, and they frequently involve pooled data limits or aggressive roaming penalties when employees travel internationally.
So they can't just have unlimited everything.
No, imagine a scenario where Apple releases a major 5 GB iOS update. If an MDM didn't restrict large over-the-air updates to local Wi-Fi, you could have 3,000 employees sitting in airport terminals across the globe, all pulling a massive operating system update simultaneously over metered 5G networks.
The company would incur hundreds of thousands of dollars in cellular overage charges in a matter of hours.
Precisely. The MDM forces the device to wait until it detects a stable, unmetered 802.1 connection before it opens the spigot for massive data transfers. The restrictions aren't just about security. They're about managing the immense financial overhead of maintaining thousands of roaming, data-hungry supercomputers.
It fundamentally changes how you look at the device. So let's trace the arc of what we've unpacked today. We started by dismantling the concept of the standalone phone, looking at how it relentlessly negotiates connections across a geographic grid of cells. We explored the paradigm shift of 5G, not just as a faster way to stream, but as an architectural leap that externalizes computational power to the cloud, allowing the phone to act as a bridge for the Internet of Things.
And we examine the mathematical elegance of how it locates itself. calculating intersection points from Department of Defense satellites and synchronizing with atomic clocks.
While seamlessly falling back on localized Wi-Fi AMAC address mapping when the sky disappears.
Right. We track the evolution of identity from a physical removal microchip to embedded secure elements capable of juggling multiple cryptographic profiles simultaneously.
Which brought us directly into the corporate management layer. The delicate, containerized sandbox of BYOD protecting your personal data, contrasted against the total dominance of the Coke model.
And finally, pulling back the curtain on the MDM console.
Right, where an administrator can enforce encryption, disable hardware at the kernel level, and strictly orchestrate network traffic to prevent massive financial penalties. So, to you listening, the next time you tap that glowing screen to authorize a Bluetooth handshake, or you seamlessly pull down a corporate email while walking through an underground parking garage, take a second to recognize the scale of the machinery around you. You are interacting with a highly structured, violently fast, and heavily monitored global infrastructure.
It is an ecosystem defined by continuous surveillance and centralized control. And analyzing it at this technical depth leaves us with a fascinating, almost philosophical dilemma.
That's that.
We've established how deeply an MBM can embed itself into a device. It can track your altitude down to the meter, alter the functionality of your camera hardware, partition your storage, and micromanage your network routing. But if a remote organization holds the ultimate cryptographic power to alter a device's functionality, or initiate a kernel-level wipe the second it drops off the network, it forces us to ask a difficult question.
I'm listening.
In an era of embedded profiles and hypervisors, does the concept of a user truly owning their hardware even exist anymore?
Man, that is a heavy, incredibly relevant thought to walk away with. The invisible architecture governing our digital lives is definitely more complex and a lot more restrictive than the marketing suggests. Thank you for joining us on this deep dive. Keep questioning the tech in your pocket, and we will see you next time.